Uh, so I'll be talking about shadow mapping today. And the basic idea behind shadow mapping is we map the entire scene through the perspective of the light source rather than the camera, and we store it into a texture. And then we do a two-pass thing. Like first, we check the depth mapped texture if the scene, the objects in the scene, the fragments of those objects, if we try to check through like the perspective of the light source, that if a fragment is occluded by another fragment, then we discard that fragment. So I mean, I know that sounds weird like right now, but I'll try to elaborate on that idea further in my slides. So this is, yeah, just basically you can see like this fragment would be occluded by this object's fragment when you draw like a straight line through the light source. So that is how it's gonna that is the basic idea basically. Something we need for shadow mapping is the knowledge of depth testing and frame buffers in order to actually implement shadow mapping. So depth testing, we have to enable it in our engine. We always enable it, otherwise we get like weird artifacts. So like I have video it displays. Oh, it does work. So this is what you'll get, something like this if you won't have depth testing enabled. And when we enable depth testing, it'll like even out. It won't be as bad anymore. So a depth buffer actually stores the value of a fragment clamped to 0 and 1. What that means is like we have the near plane and the far plane, and the depth value is actually the normalized value of the near plane and the far plane between 0 and 1, and that would be stored in the depth buffer when we enable depth testing. I was just getting confused on what a fragment is, so I just wrote that there. Which is, fragment is data necessary to generate a single pixel when it passes through all the stages of the like from the start of the fragment to when you actually do it, when it actually comes in the fragment shader, and then it's thrown out of there. That's what a fragment is. It's basically a pixel after it went through all the stages. So, sorry. So the idea here is that we are gonna, like, if there is a fragment here, and we are first gonna store the depth map from the light's perspective, and then we are gonna actually perform a check which will say that if this fragment is visible, if like it's not occluded by any other fragment in front of it, then we'll say, okay, this fragment is not in shadow, but clearly here it's occluded, so the check will return negative. It's basically, we're going to check if the distance, the closest distance of a fragment in the current depth map is like less than what the current fragment is. I'm sorry, I think I'm getting things a bit mixed up while I'm saying them. It's basically this fragment here, we are gonna actually try to see if it's behind or in front of the other fragment from the light's point of view rather than the eye's view. We are going to tally that through the depth map. So a depth map is depth of all the z values rendered from the light's perspective stored in a texture. And for texture, for storing the data of a scene in a texture, we need something called frame buffers. We already use frame buffer, which is the default frame buffer, which combines the various color, depth, and stencil buffers. And in the combination of these buffers, is what is frame buffer, but OpenGL allows us the ability to render to a different frame buffer than the default frame buffer, which allows us to actually what this allows us, like right now we always render to our screen, main screen, whatever we do in the engine, but we can actually take the the information from the screen and then store it in a texture and then use that later in order to determine if things are occluded or not. So frame buffers have some requirements. So the thing is, we have to at least attach one buffer out of like color depth stencil. But even if we attach, like let's say depth, we still need a color buffer. So we'll have to have like both color and depth at least for this shadow mapping demo that I'm gonna do. So this is basically how you create a frame buffer object. You just, it's like very standard with other things in OpenGL as well. You just first generate the frame buffer, then bind the frame buffer. This is not really, these two lines are not really about how to create it, but this is basically trying to check if our frame buffer is complete from the last slide. Like if these requirements are met, then we can like actually test it if it's met, so using this condition. And then we gotta reset to default frame buffer so that we can actually render our screen. So basically we'll do these things and store the information in a texture map, depth map or a shadow map, and then we'll start rendering our scene as usual. So that is. And this is basically how you would attach a texture to a frame buffer object. So in the previous slide we generated the frame buffer object, and now we can actually use, I think I mean this should have been texture here because I'm trying to use that, I mean I just like mixed up the variable names, but basically this is how you would attach a texture to a frame buffer. I'll go over all this in the demo to like actually show where the code resides, but this is just an example to show you up front. Now this is something, this is light space transformation. What we are going to do is use orthographic projection. So what that means is instead of, so when you're doing the scene right now, we are using perspective projection, orthographic for our 2D. So, but like this projection doesn't relate to that. This actually relates to the projection of the light source itself, the light caster. And so because I'm going to use directional light in this demo, it's going to be an orthographic projection. It is an orthographic projection because for perspective projection there are some more little quirks which I didn't go. I mean I can go through them as well. We have to just. It's basically that the depth values are not like linear when you do perspective projection. But when in orthographic projection, because the planes are parallel, the far and near, they're sort of linear. So you don't have to do a little shift. You don't have to change the depth map too much in there. But the basic idea is we get the projection, the light space matrix, which is the light projection frustum and the view, and then we send it to the GPU. So I'll go over this light space in the code. So I'll try to go over the demo of this. This demo is basically us, me trying to, or like not even me. This is not my demo. I'd like got it online, but I tried to understand it. So I'm gonna relay that information now, what I understood from it. So just like earlier, this demo is basically trying to see how the depth map would look like from light's perspective. It's not actually producing the shadows. So the first thing we do is like generate a frame buffer, like I said, like in the slides, and then we'll attach this depth map texture component to it, which will have like a width and a height, and after attaching up. So like this is actually just creating the depth texture, and this is where we attach it. So this depth map is the same as this, and then we actually bind the frame buffer. Then we reset. I'm sorry, I'm getting a bit confused. So we basically in here create the depth texture and attach the texture to the depth buffer, and then we do this draw and read none, because we don't want to draw to this texture or read. I mean, we don't need to render any data. We just are trying to test the depth here. This is the uniform that will go in the depth map that will come in here, and this is the light space matrix that I talked about, which will have the lights projection and lights view, and which will just come from this GLM there, the OpenGL's math orthographic and look at function that this demo is using. And here is something that's a bit important. It's that first, the viewport, when we actually are trying to render to the depth map rather than the actual screen, is going to be the width and height of the shadow. But once we are done with that, we are going to render the scene, which is just basically a floor and 3 cubes. And then we are going to bind the original frame buffer. This is basically for when you put 0 here, it's like it will bind the original frame buffer. Here I bound the depth map frame buffer object, and then I have to reset the viewport to like actual screen width and screen height. First, the viewport is the shadow's width and height, then later it'll be the original screen width and height. And then I'm just gonna use render like to a quad on the screen to show you what the depth actually looks like as from the perspective of the light. So once I run this, these are basically 3 cubes in here, and you can see like the grayscale signifies the actual depth value, and in the shader, if I can go in the shader, it will be the actual depth value is just being outputted by the fragment shader. So I can even like do something like it'll just like change the color of it a bit. So I can just to show that it's like the depth value. And so this is up to when we are gonna store the value in a texture map. After this, what we are gonna do is actually trying to render the shadow with like now we have the depth map, so we can try to go through the actual algorithm how shadows are generated. So now I'm gonna just switch to the other demo I have here. So just so in the actual shadow mapping, you'll see like the last demo, it'll be like much of the same code, but instead of rendering to a quad, you're actually gonna take the view light projection and like render to the actual scene instead of rendering to the quad, just to showcase how the depth looks like. So it is the same thing. You generate the frame buffer object, you create a depth map texture, and the depth map, the frame buffer object, and we send the shadow map in to the fragment shader again, and the diffuse texture is for actually the lighting, which is not. I mean, it has to do with shadowing, but that's not where the shadow calculation gets affected. We again send the light space matrix, which is again the matrix where you look at the world through the light's perspective, and after that, this is when we are saving it to the actual texture, and after that, for rendering the scene as normal, we take the projection view of the actual camera, and then we send them like this is business as usual. We always do that in even our engines, and that is it for the. It's the same code for not in the shader. Shader code is much different than that. In the shader, the actual light space matrix is going to come in, and I'm going to send from the vertex shader to the fragment shader that light space matrix. Yeah, so frag position light space, it comes in here from here, and but after all the lighting calculation is done, I try to calculate the shadow, which is the light space position of the fragment. I send it to the shadow calculation algorithm, which takes the coordinates, and this is something which we do not require right now. It will work without this as well, which is just this is a perspective divide which automatically happens if we do something like if we pass stuff to the GL position, but here, because I'm not passing it, I have to do it myself. So this is that, and this is basically transforming it into 0 and 1 range, which is the depth range, rather than the NDC range, which is -1 to 1, which is normalized to its coordinates. And this is the signature of a texture function in GLSL, which can actually give me the closest depth of the shadow map, and which would be the slide I showed, in which it will determine if there is something closer to the current. Some closer fragment already occludes the fragment that I'm analyzing. So if that is true, if the current depth of the fragment is greater than the closer depth, then I send one out, which will just basically there would be no shadow then. But otherwise it means it's occluded, so there would be shadow. So that's basically a check there. And so if I'm going to run this, there's going to be shadows here, but with artifacts. So this is like a moire pattern, and but you can clearly see there are shadows in here, and so this works. Now, so like this is not good. We gotta improve this shadow acne, and this kind of took me a while to understand. What's going on here is actually in our shadow map, the texels, like that's why I wrote it all here. It was kind of complicated. The texels have a limited resolution, which is in here. I have done like 1024 by 1024. So the texel actually, they said that like if the lines are up, down, top, then it doesn't really affect. But if it's like slanting, if the light rays are coming from a direction, the texels are actually bigger than than they should be, and so like some of them like stick down in the bottom, and we get like this kind of black lines, which makes the Moiré pattern. And there is basically a very simple fix for this. Is like you just give your shadow map a bit of an offset, so it never actually goes below the surface, any surface. So for that, this is what you have to do. You just like give it a little bit of bias, and it will never go below the surface, and there won't be a Moiré pattern. So I'll just try to do that here. And the pattern should be gone after that. Okay. I think I messed. Oh yeah. So the pattern is gone now, and it was just like a little bit of float bias. Something to keep in mind though, this works for the scene right now, but this bias won't really work if like the slant of the objects is not constant, maybe like a sphere or anything. So basically you would want to calculate the slope of the object like on the fly. For that you can like calculate the bias by, it won't like, right now you won't be able to see, but this is a better way to calculate the bias. It'll produce the same results for now though. Other than that, there is one other problem in the scene, which is we are seeing these, like, why is this in shadow now? So that is because the frustum of the actual projection of the lights from the light source is only like certain length. It's in here it's only like -10. Sorry, this near plane and far plane here. So the frustum is limited. So anything outside the frustum is actually getting like a larger value than 1. So it at the end it like kind of wrongly assumes that it's in the shadow. So if we just like limit it to less than 1, then that should solve the problem of the shadow that is wrongly being casted behind the objects. So we can fix the oversampling like that. And I basically did all this from this one website, and that is my presentation.
So, how is the resolution of your shadow map affecting the render?
It's kind of difficult for me to even visualize that, and I tried to like read on it again and again and try to see, but it's basically
So like there you have the shadow width, shadow, let's go back to, you can go back to your program.
okay.
You have the shadow width 1K and the height 1K. Make it 256 by 256 right now.
It will change the Moiré pattern a little, but it won't. First of all, I need to not include
Where
the
are we?
bias.
That won't work?
Huh?
You can't leave that in there?
Yeah, that was just to show guys. I don't think that will work. Because this is the code without the bias now. So the lines got thicker, and if I change it even, I don't know, I have not tried this.
Why don't you just like leave the...
No, but leave the rest of the code there.
Yeah,
Yeah.
you don't have to change anything else.
Yeah, I'm just curious, what does the size of the map affect?
I mean, if the resolution is bigger, the offset, the needle also needs to be bigger.
Well, you should see start seeing staircasing on your shadow.
So put back your bias and then look at what the low resolution shadow map does.
Because this is the perpetual problem with shadow maps, is that how high res do you render your light source with shadow map? You know what I mean? So there's this trade-off. If you sit there and render really high res, the shadows looks nice, crisp, and clean. But if you go small, then they start going jaggy, edges on your shadows. And you're like, oh, wait a second, my shadow has jaggy edges. Stair stepping. So that's what I wanted to see.
It's like, from what I read, it said that the pixels of the shadow map itself are bigger than the actual.
He's not talking about the shadow acting, he's talking about the edges of the shadow.
Oh,
So yeah, so
okay,
put all
okay.
your bias back.
Okay, yeah.
That doesn't need to speak about.
Oh, I get it. What
It
you're
should just be
talking.
big out there, like your shadow's like zoomed.
Yes, but also the bias needs to be bigger.
Yeah, bias makes it.
Yeah, but he has an auto bias.
Do the better bias one.
Do the auto
He has
bias.
an auto bias. Right.
No, the auto bias is also like hard coded, then
No, it changes depending on the fragments,
Yeah.
normal and direct,
Yeah.
light direction.
no, but then I mean the 0.05.
Oh yeah, so
That's
so if we increase bias,
Let's see what it looks like. Let's go.
See that one work now.
Okay, no, so
Oh.
now zoom on the shadow.
Alright.
Let's go right down. Let's go right down.
huh? This happened because of the texture resolution. Actually, I think so. This one.
I'm expecting, see like right here? See how this, right? This is in the middle of the body, right? And now, we'll look at this picture right here. Now go up the res.
Uh-huh.
You can actually see that in the original resolution.
Well, let's just see. That's fine, yeah, I think go.
You can still see it.
No,
Well, this
not, you
stair-
see, it's a totally different pattern, but you can see the stuffing.
There's not power up to for the
No, you
map
see-
or does that not matter?
Because
That
the,
is induced by the bias.
Yeah,
This-
the offset has to be like go with the bias. I mean the resolution. You know,
Mhm.
1024 resolution is perfect with the 0.05. It seems right now. So if you like increase the resolution, also like lower the bias a little bit.
Well, here, move it to 1024. Right? Everything was set for 1024. That's what you had.
The stair stepping will still be there.
Yeah. Okay, that's stair stepping, right? This, right? That's proportional to your resolution of your shadow map. And this is where the shadow map, this is its Achilles heel. It's a very fast and very cheap way to do a shadow. Because what shadow mapping is doing is basically remember, everything in graphics is there's the right way to do it, then you try to cheapen it and make it faster, right? And so when you cheapen it, you have trade-offs. The trade-off is we should be doing ray tracing, right? That's the right way to do shadow maps. Just do shadows. We're not doing that. We're doing this cheap and cheesy. Let's render the scene from the camera, the light perspective, and take the depth buffer as to indicate what's in shadow or not in shadow, right? And the side effect is the illusion falls apart because you can see the stair stepping. The way to reduce that is if you now increase your thing to 4K by 4K, the steps will be there, but they'll be a lot smaller.
And like other techniques are there as well, like point shadows and omnidirectional shadows, in which they actually take a cube. I don't really know, but like it looks much better. I have the demo running. I didn't understand it much. But-
Blur the shadow.
Huh?
Blur the shadow.
Yeah, exactly. That is another technique which is called PCF, but I was running short on time, so I didn't include it. I could blur the shadow as well. And I have the demo even right now.
A cheap way to blur the shadow is you render it, and then you shrink the shadow map down 10 to 20% with bilinear filtering. And then that's going to smear it right off. Maybe a little more fuzzier on the edges, but it'll smear it.
Yeah, that's fine. I mean, compare it to,
It's like an anti-aliasing effect.
Yeah, yeah, that's okay.
Cool. Other questions? Cool. All right, thanks.
I just think I don't think you can explain more by just showing us demo than showing us the code. But I like it. Really.